Hello friends, welcome to our online lectures on detection and estimation theory. And this is going to be our 15th lecture, which is going to be a continuation of the random signal detection. Whatever we have discussed, I'll talk something more about those derivations that we did, and see what we can do further in random signal detection. So in the last class, what we discussed was that we took two hypotheses, again a simple hypothesis testing problem, a simple hypothesis testing problem we took, and here the hypothesis H0 was just the noise, Xn is Wn. The noise we considered was a wide Gaussian noise with mean 0 and variance sigma square. Right, the noise samples were uncorrelated. The signal part H1 statistics was Sn plus Wn, where now Sn we said that it was drawn from a Gaussian distribution with mean 0 and covariance matrix was given as Cs. Right, and the number of samples that were with us was 0, 2, capital N minus 1, so we had n samples. And then we also derived the optimal detector in such a case. The optimal detector we figured out was our Tx is equal to X transpose S hat greater than some threshold, let's say lambda dash, to decide H1 hypothesis to be correct, where S hat was called as the estimate of our signal and which was given as Cs times Cs plus sigma square I inverse X. Okay, so this is what we discussed in the last class. So overall I can write my Tx to be X transpose Cs plus sigma square I inverse X. Okay, so this was our estimator. We know it was a MMSE estimator, and this particular entity is called as estimator correlator. Okay, so we also drew the block diagram where we took Xn, passed it through a Wiener filter with response Cs plus C square this inverse, then multiplied it with our signal Xn. So this was our S hat of n. Then we summed it over from n is equal to 0 to capital N minus 1, and then we passed it through a detector. Okay, so this was H1, this was H0. Okay, so this we called it as a Wiener filter, or you can call this as an estimator. So this is our estimate for Sn from Xn. Okay, now I'm going to take this further. Now you can see here that we can write this Cs. Cs can be decomposed into an eigenvalue decomposition. So we can do an eigenvalue decomposition of Cs. Okay, what I mean to say is that I can write this Cs is equal to V transpose Cs, I can write V lambda S V inverse. Okay, so what are these metrics? So these are all matrices. So our Cs is a n cross n matrix. This is also all our n cross n matrices. Okay, now V is called as the eigen vector matrix. So V transpose is identity. This is the property here. V transpose comes out to be the identity matrix. The lambda S is called as the diagonal matrix. So the elements of this diagonal matrix are the eigenvectors, eigenvalues of matrix CS. Okay, so the diagonal elements are eigenvalues. Okay, and corresponding to these eigenvalues, what matrix you get, this V matrix. So corresponding to, let's say there will be n eigenvalues. Let me denote it as lambda is 0, lambda is 1, lambda is 2 till lambda s of n minus 1. Corresponding to each eigenvalue, we will have an eigenvector. So let me write it as Vs0, this is Vs1. So these are all vectors and so on. So these are unitary vectors. Okay, so that means the norm of these vectors is 1. Okay, so V transpose V is equal to 1. This is what we mean. And how we form a V vector? V vector is just the composition of these eigenvectors. So Vs0, Vs1, Vs2 and so on. Okay, there are other properties of these eigenvector matrix V. The other property is called is that V transpose is equal to V inverse. Okay, so this is another property of this eigenvector matrix. So we have this CS, which is a symmetric matrix, symmetric square matrix, and it can be written in this form. It can be written in V times gamma S times V inverse, where V are the eigenvector matrix and lambda is the diagonal matrix. So let's go back. Now I'll show you how to use this matrix here. So let's see this expression again. So what I can do is, so let me write it here. So T of x is equal to x transpose CS plus sigma square I inverse x, right? Now here you can suppose there is an identity multiplied by identity here. There is another identity multiplied here, and suppose there is another identity multiplied here. So we know that V transpose is equal to identity. V transpose V is equal to 1. So okay, so these are vectors. So this will become identity, this will become 1. Okay, so what we are going to do is, I am going to replace identity with this form V transpose. So I can write here as x transpose. I can write this as V transpose. Sorry, V's are the vectors, so V are the matrices. So let me write it as V. I'll skip the bars. Okay, in fact, yeah, so V transpose V is also identity. I'm sorry for that. So here it is a vector. Okay, that's why CS times V transpose CS plus sigma square I inverse, then I can write V transpose X. All right, now what I can do is, let's suppose my Y vector, let me define my Y vector as V transpose X. Okay, I'm defining this vector. So what is going to be my Y transpose? Y transpose is going to be X transpose V. So I can replace here this part with Y transpose, this part with Y. So let me do that. So this is Y transpose V transpose CS V transpose CS plus sigma square I inverse V times Y. All right, now you can see here, according to the eigenvalue decomposition, if you see this equation here, if I multiply both the sides by V inverse, what I'm going to get is V inverse CS is equal to V inverse V times lambda s times V inverse. This is identity. Okay, so this is identity. Let's forget about it. Let me post multiply both the sides by V. All right, so if I do that, so I can multiply this and this both the sides. So this is again identity. So what I am left with is V inverse CSV is equal to lambda s, or we know that V inverse is equal to V transpose, so I can write V transpose CSV is also equal to lambda s. Okay, so here I'm going to do the same thing. V transpose CSV is what? It is lambda s times V transpose CS plus sigma square I inverse V times Y. So what we can do is we can take this part here and consider it of the form A inverse, B inverse, C inverse. So what I'm going to do is I'm going to write this in the form CBA whole inverse. Okay, so let me do that. So this becomes Y transpose lambda s times, I can write this as V inverse CS plus sigma square I times V transpose inverse whole inverse times Y. Alright, now V transpose inverse is equivalent to V and V inverse is equivalent to V transpose. Okay, so this part I can write it as Y transpose lambda s times V transpose CS plus sigma square I times V inverse Y. Now let me take this inside, so it will become V transpose CSV plus sigma square times V transpose V whole inverse Y. And we know that the V transpose CSV is again lambda s plus this is identity, so sigma square identity inverse Y. Alright, so this is what we get when we use the eigenvalue decomposition of CS matrix. Alright, now what is the advantage that we get here? The advantage is that if you see this particular matrix here, this is a diagonal matrix, this is again a diagonal matrix, so the inverse is also going to be a diagonal matrix and multiplied by again a diagonal matrix, so this whole quantity here is a diagonal matrix. Okay, so this whole quantity here is a diagonal matrix, and I can also write the value also. So the value of this diagonal matrix, each of the elements will be equivalent to lambda Sn over lambda Sn plus sigma square. Okay, lambda Sn and sigma square come from here, inverse is upon, and this is lambda Sn multiplied. Okay, so the whole thing, this Tx, this is Tx, right? So the Tx can be written as summation lambda Sn over lambda Sn plus sigma square times y square n. N goes from 0 to capital N minus 1. Alright, so rather than doing a complex matrix multiplication, what we can do is we can first process our signal xn, and then we take the energy of those symbols y square n and then weigh it corresponding to the eigenvalues and then sum it over. Okay, so this form is called as the canonical form of the detector. So what is my y vector? Y vector is my V transpose x. Okay, so I can draw it in a block diagram. What I'm doing is I'm taking xn and then I'm finding I'm decorrelating. So this is called a decorrelator, which will give me y vector, which is V transpose x vector. Then I take this. Then what I do is I do a squaring of it. So here I get y of n, here I get y square of n. I multiply it with lambda Sn over lambda Sn plus sigma square. Alright, I multiply it, then I sum it over from n goes from 0 to capital N minus 1, and then this is my test statistics that I get, and then I form a decision using the threshold mechanism. Okay, so this particular form is the canonical form. So in this you do not need an estimator. This is a different form of just of the same thing. It is in a different form you can get the same thing. So this was our estimator correlator. All right, so this was our estimator correlator. And the second form that I discussed, when you do a eigenvalue decomposition, then you get a canonical form, something like this. Okay, now let's move further. You can also so in this particular example, what we took is that we took the hypothesis xn to be wn, and wn were considered to be wide Gaussian noise. Okay, wide Gaussian noise. But rather than this, you can also take a colored noise. So you can take it to be a Gaussian process now with covariance CW. H1 remains the same, which is xn is equal to Sn plus wn. Sn again is colored Gaussian noise with mean 0, variance sigma, variance Cs. Okay, and in a very similar way you can do the analysis, and I'm directly writing the result that we get. So this I'm giving you as an example, as a exercise. You find out the result. I'm directly writing the result. Comes out to be Tx is equal to x transpose Cw inverse Cs plus Cw inverse of x. Okay, and this is this is our estimator. S hat is our estimator. Cs times Cs plus Cw inverse x, and this is called as Cw inverse is called as a pre-whitening filter. Okay, so this pre-whitening filter we did it in one of our earlier lectures. So what we'll do is we'll first find out the estimate of the signal, then we will whiten our signal, and then we multiply it with the x transpose here. All right, so this was another variant I'm giving you as an exercise. You please do it at your places. Let's talk about one more generalized version of this particular detection. So this particular problem, let's take a very general case of general Gaussian detection. Here what I'm going to consider is that the H0 is again the same thing, Wn is again a colored Gaussian noise with mean 0, variance Cw. Now I'm going to take my signal to be a non-zero mean Gaussian. So let me take my signal to be non-zero mean Gaussian. So let me take it to be mu of s. This is a vector, and then C of s, which is a matrix. Okay, Cs is a covariance matrix. And for this case, let's figure out what is going to be my NP detector. So let me do find out an NP detector for this case. So what I'm going to do is I'm going to find out the likelihood of x given h1 divided by probability of x given h0. This is my likelihood test. If it is greater than some threshold lambda, I detect it to be h1. All right, so let's write down the probabilities of these particular matrices. Okay, one thing to note here is that my xn is distributed in the similar fashion. So this is n0 CW. My xn under hypothesis h1 is distributed, so the mean will shift now. Mean is mu of s, and variances, as we know, covariances add up. So this is cs plus cw here. So my Lx comes out to be 1 over the first quantity, 1 over 2 pi power n by 2, determinant of cs plus cw power half times the exponential of minus half x minus mu s transpose cs plus cw inverse x minus mu s, right, divided by the likelihood of under hypothesis H0 is 2 pi power n by 2, determinant of CW power half. This is exponential of minus half. Mean is 0 here, so it becomes x transpose CW inverse x, and this is to be greater than lambda to decide hypothesis H1 to be correct. Now let's solve this. So what I can do is these two will cancel out each other. I can take this particular quantity to the other side. I can take the log. Okay, I can take the log. So this particular quantity comes goes to in the numerator. So I'm directly writing it. This is lambda dash, and this particular quantity we get is half of x transpose CW inverse x minus x minus mu s transpose cs plus cw inverse of x minus mu of s. Alright, so this is what we get. I can also remove the 2 for the time being, or if you want you can keep it. Let me keep it. Let me expand this bracket here. So this becomes x transpose CW inverse x minus x transpose cs plus CW inverse x plus it will be x transpose cs plus CW inverse mu of s plus mu of s transpose cs plus CW inverse of x minus mu s transpose cs plus CW inverse mu of s is greater than lambda dash for hypothesis H1. Alright, now here you can see I can combine these two entities here. So let me write it half of, so this becomes x transpose CW inverse minus CS plus CW inverse of x plus, now you can see these two quantities are same. Okay, if you take the transpose you get the other one, so I can directly write it as 2i's of x transpose CS plus CW inverse mu of s, and this particular quantity is a constant. I can take it to the other side, so let me put a lambda double dash, and this is my test hypothesis. So this is my t of x in this particular case. And let me further simplify it. I can approximate again using the same matrix inversion lemma. I can write this particular quantity as CW inverse CS of CS plus CW inverse. Okay, I've just used this matrix inversion lemma. So this turns out to be half of x transpose CW inverse CS plus CW inverse of x plus x transpose CS plus CW inverse of mu of s. So this is our whole thing here. Now you can see it comprises of a quadratic term as well as a linear form in X. Okay, so we'll take two cases here. One case is, so you can take the first case, case 1. If CS is equal to 0, CS is equal to 0 means that the variance is 0, variance is 0 of the signal. That means the signal becomes deterministic. If this is so, then what is going to happen? Here you can see it is CS, so this quantity goes to 0, and what I am going to be left with is only X transpose CW inverse of mu of S. And you know that this was our case for a pre-whitening plus a matched filter. Pre-whitener and a matched filter. Okay, so it's very simple to see that case 2 was if you, let's say, if my mu of S is 0, then what happens? This second quantity becomes 0. What we are left with is only this expression, and this is what we derived in our earlier problem in this lecture. So this turns out to be half of X transpose CW inverse of the S hat vector, where this is my estimator and this is my pre-whitening filter. So this is pre-whitener plus a estimator correlator. All right, so this ends our discussion on the detection of random signals. What we meant here is that we knew the distribution of the random signal. We didn't knew it what exactly is the signal, but we knew the distribution, and we had full information about these distributions. Okay, so you can practically take any other distribution. For example, Sn is not just Gaussian, but it could be any other distribution, and then you can follow a similar procedure and obtain the optimal detectors in such cases. All right, so this was all about the random signal detection. We extensively made use of the likelihood ratio test or the NP detector to get our results. In the next class, what we are going to do is we are going to look at so it may be possible that some of the parameters are unknown in these detectors. Suppose if I'm taking this particular example, it may be possible that I do not know C of W or C of S or mu of S. Some of the parameters of the PDF is unknown to us, and we will see then in those cases how do we detect a particular hypothesis. I'll stop here. Thank you very much.